insights that we just gained about the modified Gram-Schmidt orthogonalization process as opposed to the classical Gram-Schmidt process is that at a given stage of the computation we've already computed Q0, but we've also updated all of the future columns by subtracting out the component in the direction of the columns of Q that have already been computed. What that means is that in the next step you compute Q1, but A1 has then already been updated with the component orthogonal to the columns of Q0, and therefore all you have to do is compute its length and divide by it. So in our algorithm here, all we have to do is compute row 1, 1 as the length of A1, which has been overwritten by the orthogonal part of A1, orthogonal to the previous columns. And then we update A1 with A1 divided by row 1, 1, where now we're overwriting matrix A with intermediate results. Okay. At that point, A1 really is Q1. So what you want to do is subtract out the component in the direction of Q1 out of all future columns of A. And what does that mean? That means that you want to compute all of these coefficients right here. Now, how do we compute those coefficients right there? Well, we have reasoned through that R12 transpose is equal to Q1 transpose times A2. Okay. And then you want to use those coefficients to subtract out the components in the direction of Q1, and that you get by saying A2 becomes A2 minus Q1 times R12 transpose. So, this particular algorithm performs exactly the same computations as classical Gram-Schmidt does, but in a slightly different order. And by doing it in a slightly different order, it turns out that we get a more accurate answer.